Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest, sum of imbalanced number of all subarrays. The problem is interesting, and as always, we will start from the very brute force solution of order n cube and optimize it to order n square and finally to order n step by step. I would encourage you to stick till the end so that you can understand the exact thought process behind the optimizations, because that's what is important and will help you in the long run. So with that, let's get started. The problem states that you are given a zero indexed array nums and you have to return the sum of imbalanced numbers of all its subarray. The imbalanced number of a subarray of an array is defined as the number of indices in the sorted array which satisfies these conditions, right? So let's take an example. Let's say the given array is 2, 3, 1, 4. So we need to find out the sum of imbalanced number of all its subarrays. So if you see the imbalance number definition, it says that I should be in between 0 to n minus 1. So basically, subarray of size 1 doesn't make sense here. So these are all possible subarrays of size greater than 1 of 2, 3, 1, 4. And as mentioned in the imbalance number definition, we have to work with a sorted array. So let's just sort the array, and the sorted array with sorted subarrays would look like this, right? Now we need to find out the imbalanced number of each of these subarrays, sum them up, and that will be the answer. So let's start with this one. So if you see, the only valid value of I is this. So if just look at the definition of again imbalanced number again, the number of indices such that it lies between 0 to n minus 1 and array of I plus 1 minus array of I should be greater than 1. So in this case, there is only one such index, and if you see, array of I plus 1 is 3, array of I is 2, so difference is equals to 1, which is not greater than 1. So this index will not be considered in the calculation of imbalanced number, and hence imbalanced number of this subarray would be 0. And similarly, the imbalanced number of this subarray would be 1. Again, there is only just one index I possible, and for this, array I plus 1 minus array I is 2, which is greater than 1, and hence this particular I will contribute to the imbalance number, and hence this is 1. Now similarly, the imbalance number of this will also be 1. Now coming to the third array, imbalance number of this subarray would be 0. There are two possible I's here, right? This and this. For this I, the difference between array I plus 1 and array I is 1, which is not greater than 1. And similarly, difference between this array I plus 1 and array I is also 1. So both of this will not contribute to the imbalance number, and hence the imbalance number here is 0. Finally, for this subarray as well, the imbalance number is 1 because only this particular I will be contributing to the imbalance number. The other I will not be contributing because the difference between 3 and 4 is 1, right? And finally, the imbalance number of this would also be 0. So in total, if you sum the imbalance number of all the subarrays, you will get 3, and 3 is the result. So hope the problem statement is clear. Now how to solve this? So one brute force way to solve this is to just apply the exact same algorithm that we have just went through. We'll go through all the subarrays, sort them, and then iterate over each of these subarray and figure out the imbalance number of each of the subarrays. So the pseudo code for that would look something like this. You will iterate over all the subarray L comma R, right? Now for each of these subarray, you will first sort the array, right? And after that, you will iterate over the sorted array and figure out the indexes which will contribute to the imbalance number, and you will just increment the result for all those indexes. Now what is the time complexity of this approach? This is a nested for loop which in which both the for loops will run for n time. So basically, the for loop will run for order n square time. Now inside this nested for loop, what we are doing, we are sorting an array and we are iterating over the array. So sorting the array would require order n log n time, and iteration would require n time. So in total, we are doing n log n operation inside this nested for loop. So in total, the complexity of this entire approach is order n cube log n, which will surely not pass given the value of n is 1000, right? Now how to optimize this? Which of these factors will you remove first, or will you try to remove first? The answer is this. Why? if you are removing n square, it means you are not iterating over every subarray, and here you need to compute something for each of the subarray. So this is hard to remove. Whereas this says removing this means that we will not iterate over the formed array again, and we will still have the liberty to iterate over all the subarray. So in a sense, the pseudocode would look now something like this. So you'll say, okay, I will now iterate over all the subarrays, right? And for each subarray, instead of iterating over the entire subarray again from L to R, I will just maintain the sorted array beforehand, and with this sorted array I will figure out what we can or what should be added to the result, right? Now with this approach we need to now figure out what will be the diff when a new element is added to a sorted array, right? So let's look at that. So let's say this is the sorted array 1 3 4 7 9. Now there's a new element r that is coming in. The value of array r, let's say, is 2, right? Now you are adding 2 in this sorted array, so 2 will come somewhere here, right? Now what will happen because of addition of 2? First of all, one new pair will be formed, right? Previously there were 4 pairs or 4 valid i's. With the addition of 2, there will be 5 valid i's. So basically one new pair is formed. Now what's happening after that? It may happen that previously some pair was good, but with the addition of 2, those pairs will now become bad. For example, in this case 1 and 3 was already good pair, right? Basically this particular, if you put I as this, array of I plus 1 minus array of I is greater than 1, and hence this pair was good. But with the addition of 2, what happens is the array of I plus 1 will now be 2 and array of I is 1. So basically this pair is now a bad pair. And similarly, this pair will also be a bad pair. So basically what we are saying is we removed one good pair and we added 2 bad pairs. So hope we are getting it. Basically what we are trying to do is we are trying to find the exact difference, and the difference lies in the fact that there will be a one new addition and there will be removals of pairs as well, depending on where or what you are adding, right? So if you are adding something, like what exactly will you be removing? If you are adding something, you need to figure out what is the previous element, right? And what is the next element. If previous element exists, it means you have just added a bad pair, so you will simply subtract -1. Similarly, if next element exists, it means you have just added a bad pair, so just subtract -1 again. So this will be the contribution for addition of 2. You are adding one new pair, you are removing one previous pair, and you are removing one more pair. So finally you will be subtracting 1 from the previous result or number of good arrays that was there for L comma R, right? So the complete pseudocode would now look something like this. We will simply iterate over all the, so you will just initialize good to 0 inside this, right? Now as and when you are iterating over R, you will insert it into your sorted array. Now after this insert, like before this insertion, you will need to check whether you have done something which removes the count, or which removes the count of valid pairs that were existing previously, right? So with that, what we have said is if array R was already present, so let's say this is the array and you are adding 3 here. So if 3 is already present, nothing will change, right? Basically if 3 is already present, you already know whatever was good with 3, that will continue to remain good. Now there is one new pair that is formed, which is between 3 and 3, and this pair is already bad. So you are adding one pair, but you are subtracting one pair as well, because this pair will be a bad pair for sure. So that's where if you are adding something which is already there, nothing will change. Now once you are adding something which is not already there, then you need to understand that you are adding one new pair, right? Now you might be removing, or you might be inserting a bad pair, or because of this new insertion, a bad pair can be formed if array r minus 1 is present. For example, if you have added 2, if 1 is present, then it is sure that you have added a new bad pair. So you'll subtract 1. And similarly, if array r plus 1 is present, it means again you have added one more bad pair. So you'll subtract minus 1 again. So this is the complete diff from the previous iteration. So whatever was true for L comma R, for L comma R minus for L comma R plus 1, same thing will be true except this particular diff, right? So we just simply add this to the diff and finally add it to the result, right? So what is the overall time complexity now? Time complexity is you are iterating over 2 for loops, which is order n square. Inside this, you are checking whether some element is present or not, and you are inserting as well. So you need a data structure that can insert an element and can tell you whether an element is present or not. So I hope you get it. Basically, this can be done very easily using a map or a set. And you can use another map or another set, and that will give you order 1 complexity. So entire complexity of this entire algorithm is order n square, right? Now we need to optimize this further, let's say. So order n square will surely pass. You can I would encourage you to code this entire solution by yourself. So let me show you the code instead. So the code is very straightforward. As we have discussed, we will simply insert elements one by one. So initially number of good pairs is 0, right? Now for each r, what we are doing, we'll check if it exists in the given set. If it doesn't exist, then it means we have some diff. Otherwise we'll not have any diffs, right? Because if it already exists, it means we are adding a new pair, but that pair is already bad, so there is no diff at all. So if that's the case, we'll just simply add 1 for the new. So if that's not the case, we'll simply add 1 for the new pair and subtract 1 if previous element exists, and subtract 1 again if next element exists, right? And finally we'll add it to the number, to the result as well. So this was the solution with the time complexity of order n square. Now we need to optimize this further. How to do that? So the way to do that is basically you have to remove either this or this, right? Now if what does it mean to remove one of these loops? It means that if let's say you are removing L, if you're removing this loop, it means for a single L you should know what all or what every R will contribute to this L, right? Similarly, if let's say you are trying to remove R from the if you're trying to remove L from the equation, you need to know that for a single R, which all L it will contribute to and how much, right? So either of these two you need to figure out. So let's see if we are able to figure this out as or not. So again, you can simply divide this entire thing into 3 pieces and calculate these 3 things independently, right? You can say, okay, in one nested loop I will just add 1, in another nested loop I will just subtract 1 if this condition is satisfied, in another nested loop I will subtract 1 if this condition is satisfied. And you can now think if you are able to solve each of these 3 expressions independently or not. So one expression is basically this part. This is you are able to, if you are able to solve this expression or not. And then second expression is you remove this 2 and you are if you are able to solve this part or not, right? And third expression is removing these 2 and solving this part itself. So if you are able to solve these 3, you can simply combine the answer and that will give you the final result. Now I would strongly encourage you to pause and at least try this entire thing once by yourself, because it's simply doing some observation and rest of it is math, right? So let's look into it. What we are doing is we are adding something if the element is not present, or if array R is not present, right? So let's say we want to remove L, or in other words, we are saying that we want to calculate something for R, for all the R's, and then I will simply club them all up and that will give me the answer. So let's say this is the R. Now you are saying that, okay, how much this R will contribute to each of the L's before. That's what you need to figure out, right? And if you are able to figure out, you can just sum them all up and that will be the answer. The first condition is saying that it will, like, we will only consider any contribution if the count, or if this R is not present before, right? So let's say you are taking this particular subarray. So in this particular subarray, R is already present, right? So R was, array of R is 9. So 9 is already present. So for this particular subarray, this R will not contribute anything, right? In other words, this R will not contribute anything for this L. Similarly, this R will not contribute anything for this L as well, because in this subarray as well, 9 exists. And in the very same fashion, this R will not contribute anything to this L as well. But now, as soon as you come here, see, you don't have any array of R at all. So 9 is not present at all. In that case, this condition will be satisfied and this statement will now execute, right? So what does it mean? It means that we need to, this R will only contribute to those else which lies after array of R in the array, or after the last array of R in the array. So this was the last array of R. So any L before this will contribute array of R for sure. So only L after the last array of R will be a valid candidate for considerations. Now for each of these candidates, let's think about this +1 first. So what you are saying is, for each of these candidates you are adding 1. And how many times you are adding 1? Basically n minus L times. Why n minus L times? Because this one which you have added, this one will be contributed to R, R plus 1, R plus 2, R plus 3, all the way up to n, right? So because this one will be contributed to everything up till n, it means you have added n minus R, or you have contributed n minus R to this particular L, right? Similarly, you have contributed n minus R to this particular L, you have contributed n minus R to this particular L, and n minus R to this particular L as well. So in other words, what you are saying is you will be contributing 3 to these 3 indexes, right? Now in the very same fashion, now let's talk about this. What does it mean? It means that you will be contributing -1 if array R -1 is present, right? So notice that array R -1 is present in this part of the subarray, right? So basically you will be contributing -1 to this and -1 to this. But this is not simply -1. Why? Because this -1 will also be carried over to all the next indexes, because you are doing plus equals to, right? So the same logic. This R will be, this -1 will be contributed to L2R, L2R plus 1, L2R plus 2, and so on and so forth. So this is also contributing minus n minus R. So this is also contributing -3, right? Now notice you will not be contributing -3 to here, because it doesn't contain array R -1, right? Now finally, this part, this says that you will be contributing -1 if array R plus 1 is present. So array R plus 1 is 10. 10, wherever 10 is present, you will be contributing -1 or minus n minus R. So here no 10 is present, like 10 is present here, but this is already out of picture because of the first if condition. So you will not be contributing anything for this as a part of this particular expression. So the same thing you will do for every possible R, and finally you will get the contribution of all the R across all the L's. You can sum them all up and that will give you the answer, right? Let's just quickly reiterate over what we have done and see what is the overall time complexity of this entire approach. The first step that we have done is we have identified the probable candidates. So we saw that because of this condition, the candidates will only be the ones where array R is not present, right? So we can simply figure out what is the last index of array R in the left. That we can do using simple hash map, right? So let's say the last index is I. So starting from I plus 1, you will be contributing n minus r, or basically plus 1, n minus r number of times in everything up till r minus 1, right? So what you can do, you can simply add plus 3 here and you can add minus 3 here, because you have to add everything in this range, right? So adding in a range can be simply done using prefix sum approach. So you can simply add plus 3 and add minus 3 here. So let's just forget about these things for now. Now what's the second thing? Second thing is present array r minus 1. So what you will say is, if any subarray contains array r minus 1, minus 1 will be contributed to that. So it is also very similar to, so let's say this is the array r minus 1 index. So if this is array r minus 1 index, it means that anything before this will contain array r minus 1. So this will contain array r minus 1, this will also contain array r minus 1, this will also contain array r minus 1, and so on and so forth. So basically the same trick what we have applied for the first thing, right? So what you can say, okay, now figure out what is the last position of array r minus 1. Now starting from this I plus 1, I will go up to the last position and subtract 1 or n minus r from all these indexes, right? So again you will say minus, you will be subtracting 3 or adding minus 3 here in this particular range. So you will add minus 3 here and subtract minus 3 here. So subtract minus 3, it means you are adding plus 3 here, right? And finally this part, again you will see the last index of array r plus 1 and again subtract minus 1 or minus n minus r in that particular range. So in this particular case there is no array r minus 1, array r plus 1, so you will not do anything. So you will do this for all possible r, and that will, and finally you will calculate the prefix sum that will give you the value at each of these indexes one by one. So contribution at this cell, contribution at this cell, contribution this cell, and so on and so forth. And finally you can sum them all this up and that will be your answer, right? Now what is the time complexity of this entire approach? Time complexity is what you need. You need to maintain two things. One is this prefix sum array. Prefix sum array you can maintain in order and time. Second, you are adding something in some ranges based on the last position of a particular number, right? So basically you are saying that, okay, what is the last position of 9, and after that you are adding something. Similarly you are saying that what is the last position of 9 minus 1, and in that range you are adding something. So maintaining last position is also something you can do in order and time with just simple hash map. So entire algorithm will now work in order and time. I would strongly encourage you to pause the video right away and try to code this entire solution by yourself, because that will help you gain much more clarity and understand in bit more depth what is happening here. So next we're looking at the code. The code is straightforward. What we are doing is we are maintaining this position map as we have discussed and the prefix sum array. Now we are saying what is the first position up till which we can found nums of L, right? So everything here is 1 based, so that if the value is 0, it means the position doesn't exist at all, right? So let's say you get this equal till position as this particular index, right? So what you have to do, you have to add plus 1 or n minus r starting from here up till here, right? So you will add n minus r here and subtract n minus r from here. So that's what we are doing. We are adding n minus r or n minus l, whatever you call it, from here and subtracting from L plus 1, or basically the current index, right? And after that we figured out what is the position of nums L minus 1 and nums L plus 1. Now if you remember, whatever is the last position of nums L minus 1, you have to subtract n minus r starting from I plus 1 up till this particular index. So basically you have to subtract starting from this particular index up till the position. So that's what we are doing. We are subtracting n minus l starting from this particular index and up till this particular index, right? And the exact same thing for plus as well. After this entire thing, we know that we found nums of L, so we'll just update the position of nums of L as L plus 1, because notice this position denotes the last position, right? So once we have done this, we can simply do the prefix sum. That will give you the actual contribution of all the R's at a particular L. Now once you get this, you can simply add this to the result and that returned as an answer. So hope this entire solution makes sense. If you have any doubts in any of the two solutions, feel free to post them in the comment section below. I will be happy to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. And I will see you in the next one. Thank you.